Adrian, who I am so curious to see how this plays out and the details behind this, because Adrian is talking about the probably impossible, aka Crypt of the NecroDancer's network code, which initially started as a DLC, or initially started as a fan project, but was brought into the game as a DLC. So take it away, Adrian.
Thank you. Hi, I'm Adrian. Thank you for having me. I'm the lead developer behind Crypt of the NecroDancer's Synchrony DLC, and I'd like to give you a brief overview of what it took to bring online multiplayer functionality to this game. So if you haven't heard of NecroDancer before, it's best described as a rhythmic, roguelike dungeon crawler hybrid. It's turn-based at its core, but it has a strict turn timer, which just so happens to align with the beat of the music. The controls are very simple. You use the arrow keys for movement, and you attack automatically if there's an enemy in the way. And a few years ago, I got very addicted to this game and stumbled upon a Steam forum thread where people were asking for online multiplayer. And the dev team responded that this is just impossible. It's not going to happen. How could you add online multiplayer to a game like this? And I saw these posts and they kind of looked like a challenge to me. So I gathered some friends from the community. We started tinkering with a prototype and built a multiplayer clone of the game. Over the course of, well, initially it was just a few weeks, which turned to months, and then years. We got carried away, and yeah, eventually the studio behind NecroDancer noticed, and today, what initially started as a little fan project is now known as the Synchrony DLC. But what did it take to get there? So let's just start from the beginning with some netcode basics. So fundamentally, multiplayer network code is about making sure that two copies of the game running on different machines are in sync with each other and reflect the same shared game state. The most common approach for netcode is state replication with an authoritative server. All clients are connected to the same server, which holds a single source of truth copy of the game's current state, the positions of all objects, tiles, variables, and so on. And whenever a client performs an action, they send a message to the server, which then runs some game logic and propagates the results to all clients in the form of object property updates. But these changes take a moment to travel across the network, from the client that's sent the key press to the server for processing and then back to all clients. This means that when you press a key, there is a noticeable delay before your character actually moves, which for a rhythm game is not really the best thing. So an alternative to this approach, which reduces the amount of data sent from the server to clients, is known as deterministic lockstep. Instead of sending state changes, the server actually just relays inputs between clients and lets them run the game logic simulation locally. If the simulation doesn't have any outside dependencies or randomness, then all clients should end up with the same game state after applying the same sequence of inputs. But this approach is also sometimes called delay netcode, especially in the fighting game community, and well, that's because key presses again need to take a full round trip over the network to the server and back before being applied to the client. So once again, there's input lag. The server has to enforce a consistent ordering between button presses across players, since the order can affect how the game plays out. And, well, once we apply a player input to the game, that's it. It's final. We can't just go back in time and unapply the action that someone else, might have performed something earlier, right? Oh, or can we? Turns out we can. That's what rollback is about. Rollback netcode takes the idea of deterministic lockstep, but it aims to additionally reduce the local delay by allowing your client to run the game simulation even if inputs from other players haven't arrived yet. We just skip processing the player's actions at first, assume that whatever they're doing doesn't affect our game state too much, and if they did press a button earlier than we did, we roll back time, retroactively apply their input, and then eventually all clients will end up on the same deterministic outcome. So a key press will directly correspond to visual and audio feedback on a local client, regardless of ping. Pretty simple, except for the time travel part. So rollback netcode can be thought of as an undo-redo system that affects the entire game. We need to take snapshots of the game, which are copies of the game state, every single time we run a game simulation tick. These snapshots need to encode absolutely everything the game needs to run. Global variables, random number seeds, tiles, object positions, health, timers, items, and everything else. Effectively, it is a save load system that needs to be extremely fast, since it's going to run many times per second during gameplay. Whenever the player is about to perform an action, we first take a snapshot of the current game state and store that in a list alongside the input that's being performed. And then we repeat this for every step of the simulation, filling up the buffer with more and more snapshots and inputs. So at any point, we can return into the past by loading the snapshot corresponding to a past turn, making some retroactive adjustments to the inputs, and then fast forwarding the game with new inputs in place so that we can resimulate with based on a different initial state. Now, traditional rollback netcode is usually designed to suit the needs of fighting games, but NecroDancer is somewhat atypical and has a bunch of unique requirements that aren't usually found elsewhere. First of all, it's absolutely critical that there's no delay for actions performed by the local player. Most rollback implementations limit the number of rollback frames and tend to fall back to delay netcode on particularly high pings, which is done for performance reasons since it's going to be quite slow to simulate 8 times as much game logic per tick as usual. We cannot afford this delay in NecroDancer though. All actions that are performed locally must happen instantly, no matter the latency, just so that players can keep the beat more easily. And relatedly, if there's a momentary hiccup in a network, like a router dropping some packets or delaying messages, players shouldn't have to compensate for this. They should ideally not even be aware that this is necessarily happening. We don't want players to run into missed beats that can be blamed on lag, so the client should be the only one deciding whether a key press has been on beat or not. And finally, every player should feel like they're playing the game in single player locally. So all monsters and other interactions with the world immediately around the player should feel like they're taking place between just the player and the monster, and should be unaffected by what other players are doing far away. So even if there's someone else dancing at light speed on the other end of the map, a slower player character shouldn't notice that and should interact with the game using the same interactions that they're used to from single player. So in our initial attempt, we considered just following the fighting game system directly, where we subdivide the timeline into distinct frames and perform rollback every single tick. But as it turns out, in NecroDancer, most frames don't really affect game logic at all. When a player presses a key, monsters respond instantly. There's no delay. They just act in response to what the player does. And the duration of a key press has no effect either. We only care about key presses and not the duration or the release time of a key. And animations are purely cosmetic. They don't have any gameplay effects. They do occur between turns, but they cannot affect game state at all. So for a sequence of key presses that looks like this, what we'd actually store in the action buffer under our initial attempt was more like that. Lots of blank space, separating very little actually useful data. So the next iteration, we thought of ways that we could compress this action buffer into just those useful input frames. And the obvious approach here seemed to be, well, we just skip all of these idle frames here and use beats as the index for the action buffer instead. So that gives us an action buffer that's completely and tightly packed with input data. And since beat maps and music playback are synced across all players, everyone should write to the action buffer at the same time to the same indices. And yeah, this worked great when we first implemented that system. But then this guy showed up. Yeah, Bard. An alternate playable character who does not follow the rules. He does not follow the beat specifically, and he disables the game's entire gimmick and just turns it into a regular turn-based roguelike. He's intended as kind of an easy mode for newcomers to the game by letting them think about their moves before they have to, they don't have to follow the beat. But his existence actually just makes things a lot more complicated in multiplayer. Since he can move at any time, his actions are just going to be completely misaligned from the beat map and cannot be reasonably mixed with inputs from rhythm-based players. If he moves quickly, like here, he's going to build up a lead in front of rhythm players. And if a rhythm player then tries to perform another move, their input is going to be sorted into an action slot that's way before all of these built-up Bard actions, and that causes an enormous amount of rollback, invalidating all of these snapshots here. And that's going to lead to significant performance issues because we have to resimulate all of this in one frame, and also causes all sorts of artifacts, teleportation of objects, because we're essentially editing Bard's past and then just stacking the same actions and inputs on top of that. So beat numbers are just not flexible enough to support having variance in rhythm modes between different players. So the solution we actually ended up settling on for the game was to take a step back and revisit the frame-based approach at first, but put a slight twist on it. We again subdivide the timeline into frames, which we just call turn IDs instead. But the big change here is that the action buffer is no longer a dense list of frames, but a sparse map that associates these turn IDs with player inputs. And they are created on demand whenever a player first performs an action for a specific turn ID. So rhythm-bound players will use the beat map to assign a turn ID to each beat by snapping the beat's ideal timing to the center, even if they're a bit early or late on a beat. The turn ID is always going to be the same for every single beat in the song. And this way, we ensure that if multiple players perform actions for the same beat, they end up sharing the same turn ID as well, even if one is a little bit later or earlier on the beat. Now, if we put Bard on here again, if the Bard player performs an input, the turn ID will be computed directly from the current timestamp and bypasses the beat map altogether. So these actions usually take place in between the inputs of rhythm characters. So you will, on most turns, you'll either have actions from rhythm-based characters or from a Bard player, but rarely from both. If a character doesn't act on a given turn, which is indicated by these little ZZZ icons here on the action buffer, that means that time doesn't actually pass for them at all. Nearby monsters don't move, countdowns and status effects do not tick down, and so on. So basically, time is completely still, and the player ideally won't even notice that there is a turn being inserted on behalf of another player. Depending on the latency, there will be moments where actions arrive out of order. For example, Cadence pressing on turn 50 here, but then Bard, because of network delay, just squeezed in a turn 49, which arrives by the time Cadence already processed this turn 50. And when this happens, we just shift all the subsequent actions to the right, insert a new slot in the buffer, and then perform some rollback to weave the action into Cadence's timeline and make things consistent again while preserving the ascending turn ID order for the whole buffer. The system also supports mixing rhythm-based characters with different tempo. For example, Bolt is a character that plays the game at twice the speed of regular characters, and that makes the game a lot more challenging. For every regular beat, Bolt gets an in-between beat on which they have to act. And this subdivided beat map essentially generates twice as many turn IDs for Bolt players compared to Cadence. On even beats, both players share the same turn IDs and get to act simultaneously. Whereas on odd beats, only double tempo characters get to act. And again, for single tempo characters, time doesn't pass during these off beats. So monsters don't move, countdowns don't tick down, and a Cadence that's not near a Bolt ideally shouldn't notice that there is a Bolt player in the game at all. So now that we've covered how inputs are processed, how does the game's rhythm mechanic tie into this? The core principle is that the client should have full authority over the beat map, and all these relevant checks should occur locally. So this makes sure that the player never has to take network issues into account while playing and can just tap to the rhythm, knowing that their actions will go through. Every beat has a window of acceptable input timing surrounding it, and as long as the player presses a movement key within that window, the action will go through, and the game advances the index of the next expected beat by 1. So here, for example, we're expected to hit beat 48. If we hit it on time, the game will accept our input, perform an action, and advance to the next beat. If we miss the window, then the game will automatically insert an idle turn, giving the enemies free move instead. And if we double tap, hitting too early, the game inserts a special sub-beat action that indicates, whoop, you dropped your multiplier, but does not move the next beat ahead by 1 index. It's important to note that this beat map state is not part of snapshots or rollback. So rollback is never going to affect the beat map. Everything is completely local, and that's how we make sure that networking issues can never cause a player to drop a beat, or at least should do so only in the rarest of cases. So with input action processing now in place, let's look at how animations work that play between turns. I mean, right now, the game would just look something like this. If we want the player to be a static sprite that teleports between grid tiles, great, that's all we need. But because we do want animations, and because no game logic can take place outside of action turns, we have to apply animations to the visual representations of players and monsters directly, without touching the underlying game state. Most entities have an idle animation loop, which is synced with the music, and we achieve this by just subdividing the intervals between adjacent beats into fractions, and each of these fractions represents a frame within the player's animation cycle sprite sheet. This is completely local and stateless. We can just update the sprite every render tick based on the player's current music playback time, which is entirely local and, again, independent of snapshots. Things get a lot trickier when it comes to movement, though. When players move around, game logic can undo and redo these moves repeatedly for the same turn during rollback. We have to find ways that to identify whether a specific move animation has already started and is currently playing, and preserve its playback state. There's a global animation timer that counts up locally for each client, and when an animation takes place for a specific object in a certain turn, like Cadence's pending move to the right here, the global animation timer is read and copied into the animation buffer for that turn and that object. During rendering, we then take the difference between the global timer and the stored animation time and use it as an interpolation factor for moving the object from one grid tile to the other with a nice in-between interpolation function. This essentially creates the illusion of movement, even though the player is actually just teleporting and storing the previous position for these animation purposes. If there's another player that inserts an action at an earlier turn ID, like Aria on the right here, this actually would roll back the move we just performed with Cadence, and then cause it to be resimulated. While Aria's move here produces a new animation and thus gets a new timer value, Cadence's move, while it's being resimulated, it's already being animated, so we don't want to override the existing animation time with a new value, but we instead want to preserve it. In this case, because a lot of time has already passed, it just looks like Cadence is teleported to the new tile again, but if this happens during gameplay with very short times between players acting and performing rollback, this should ideally result in the animation continuing to play seamlessly, even though technically it's being reverted and reapplied many times per second. So in order for this system to work, we have to assign unique identities to each animation event, which typically consists of the entity being moved and the turn ID at which the move took place, plus some animation name so that we can distinguish different types of movement animations that might apply to the same entity. It's important to preserve this identity and make sure it's stable, because if this identity changes for some reason, then the animation would restart. So we can't just put something like the index of the move happening if there's like a global counter that starts at 1 and every time an object moves, we increment that counter. If rollback causes that counter to be shifted around, then all animations would get scrambled and things wouldn't look quite as smooth. So stability for these animation IDs is important here. And this kind of relates to sound effects, which are internally treated very similarly to these move animations. We store some information outside of snapshot state to make sure that we can track whether a sound effect is being replayed within a resimulation of the same turn. In this example here, Cadence on the left hits this skeleton to the right, knocking it into Aria and dealing damage to her. How rude. This causes 3 sound effects to be played: Cadence's attack noise, the skeleton's hurt sound, and Aria's hurt sound. Each of these sounds is played using the game's audio system and stored in the sound list for the current turn, because this is the first time these sound effects are playing in this turn. But in the same beat, we actually receive a packet from Aria that she's also making a move in the same turn. And in this case, she's attacking to the left. To apply it, we first roll back the game state to just before Cadence performed her action. And in doing so, we actually set a flag on each of these sound effects as marked for stop or awaiting recurrence during rollback. Aria's move attacks the same skeleton, and because players always out-prioritize monsters, she goes first and didn't actually end up taking damage from the skeleton at all because of that new action. So Cadence's attack and the skeleton's hit still have their previous sounds because these events still took place and they are allowed to continue playing. But because they are already in the turn sound lists, they won't be played on the native audio system a second time, which would just duplicate the sounds. There's still probably audio coming through the speakers from that initial playback event. So we just mark them as recurred. And there's some new sounds, Aria's attack and the skeleton's death sound. So they are added to the buffer, and because they're new, they will be played to the native audio system as well. But notice how Aria didn't actually end up getting hurt. The skeleton didn't hit her, so the hurt sound shouldn't actually be playing at all. At the end of the turn, any remaining marked for stop sounds that didn't recur during rollback will be cut short, and that's especially important for long, drawn-out sounds like player deaths or boss phase transitions. We don't want players to have any misleading audio feedback if rollback changed the outcome of a significant event like this. Now, with most of these technical aspects in place, there are still a few factors that can influence how a game with rollback feels in practice. Generally, it's important to minimize the impact of mispredictions and direct interactions between players in the same turn. And a pretty good example of this that we ran into very early on during development and playtesting are player collisions. NecroDancer's original local co-op mode had player collisions. You weren't allowed to occupy the same space as another player, so we just carried this over because, well, we wanted to retain gameplay accuracy. But there's always going to be some order in which player actions are evaluated with respect to each other, and we chose to prioritize players who hit early on the beat before those who hit late. And in our example here, Cadence on the left presses her movement key a bit early in the beat and Aria is a bit late. But because their actions don't conflict, rollback doesn't actually change how the actions play out when the remote inputs arrive from the other player. Now, if both players want to step on the same center tile, though, it's a different story. Only one of them will be able to occupy this tile in the end, and the other player will just collide with the one who stepped on it first. In this case, Aria was first to press the movement key, and she immediately sees herself stepping on that center tile. But before the input can make it over the network, Cadence also presses a key and sees her own movement succeed. Now, because Aria's input timestamp is lower, she gets priority here, and the result is that Cadence's input actually just gets rolled back without being reapplied, because Aria's input actually got processed first. On Cadence's screen, it looks like she just got shoved off the tile by Aria after a short delay, and that's quite disorienting, because your player already moved, and then your move is kind of changed into something else. On Aria's screen, it's not quite that bad. Cadence just harmlessly bumps into Aria after the move, so that's not really a problem. But definitely we wanted to solve this because it kept occurring far too often in our playtests. So we tried a few approaches, but we just stuck with the simplest one. Players don't collide with each other. We just disabled this mechanic altogether. The narrow corridors of Crypt's procedural dungeons make it really difficult to get out of each other's way anyway, so we also saw this as like a quality of life change. And yeah, after doing this, players no longer interrupt each other with rollback, and this just makes everything a lot smoother when moving around, even when there's a high latency towards other players. Now, there's another edge case though, even with this tweak, which can arise if two players try to attack the same enemy. In this case, these green slimes here have a single hit point, and one attack will take them out right away. Now, both Cadence and Aria press a movement key towards the slime, performing an attack, and again, Aria is a bit faster this time, and hits the slime first, followed by Cadence a bit later. And both players see the attack go through on their screen, while waiting for the other player's action for that beat to arrive. Now, once Cadence is notified of Aria's attack, the slime is resurrected via rollback, and then actually retroactively killed by Aria instead. And because Cadence's action was a tiny bit later, the right arrow key that initially was an attack now suddenly counts as a move. And from her perspective, it just looks like she got teleported onto the tile the slime was standing on a short time after attacking it. And that's not great. On Aria's screen, it doesn't look quite as bad. Cadence just kind of moves onto the tile that the slime was previously occupying and picks up the dropped gold. To eliminate this ordering dependency here, we actually introduced a special invisible object that is dropped by any slain monsters, and we call this a tombstone. It's invisible normally, but we've made it visible here for the demo. So as soon as Cadence hits the slime, the tile isn't freed up right away, but it's blocked by this tombstone. And same happens for Aria. because Arya again attacks before Cadence's input arrives. The down input is also interpreted as an attack at first. Now, both players are trying to push towards the same tile again, but this time, the slower character actually just ends up attacking the tombstone instead. So Arya is prevented from moving down even though Cadence's attack has already killed the slime. For both players, it just actually looks like the other player is attacking thin air on the empty tile that the slime was previously occupying, which is a lot better than having their position suddenly changed and moving to an unexpected position. At the end of the turn, the tombstone is despawned, and then both players can move onto the tile on the next beat. So, after addressing all of these technical and design challenges we've encountered throughout the project's development, how does this all look in practice? Well, looking at this short clip from Synchrony's launch stream, it looks like everyone's enjoying themselves in the absolute chaos of a 16-player lobby. The rollback system was initially designed and tested for up to 8 players, but people were very quick to find out how to bypass the player limit. And yeah, larger lobbies like this were a very, very common sight. So ultimately, I think we achieved our goal of bringing online multiplayer to a game that was never meant to have such a feature, and while it took many years to get to this point, the journey was well worth it. So with that, thank you so much for your attention. Huge thanks to Grimy, Private, Snowball, and the entire Synchrony team for all their amazing work. To Brace Yourself Games for the openness towards accepting such a fan-made passion project like this and inviting us to collaborate. And thanks so much to everyone who's organizing Roguelike Celebration, hosting this conference, and giving me a chance to talk about the inner workings of something I'm so passionate about. There's a lot I'd love to go into more detail about, but then that would probably stretch this talk to a few hours. So how about some questions instead?
Oh, yeah, Adrian, what an incredible talk. That was so cool, and great job on solving problems and also just limiting scope when needed to, like just maybe they don't need to collide. That was wonderful. And also your slides, everyone cannot get enough. I think it would have been hard to parse your talk without the incredible slides. So thank you so much for bringing that along as well, specifically for talking about time travel. It was very helpful.